Okay, for this part of the experiment, you're going to set up two multimeters. So if we look at the circuit, we have our DC power supply. So we're going to have a steady current coming out. And so the positive terminal is the red terminal. And so it's going into a multimeter that's set up to measure current. So it's on a 200 milliamp scale, which means the reading you're going to get is going to be in milliamps. Keep that in mind when you set up the table. You're going to want your current in amperes, not in milliamps. So then you follow the current out of the multimeter that's measuring current, and that goes to one leg of the resistor. And then the other leg of the resistor goes back to the power supply, completing the circuit. And also what you'll see here is that we have another multimeter connecting one of each leg connected to each leg of the resistor. So you're going to be measuring the voltage across the resistor. Now, standard store-bought the resistor is an example of a linear device. Its resistance remains more or less constant as you put current through it. And the next example will be a device whose resistance changes as you put current through it. But the device should remain constant, so when you plot voltage versus current, you should get a straight line relationship whose slope equals the resistance of the circuit. So we're asked to get 10 measurements between 0 and 15 volts and record the corresponding value of the current. So we are going to start with 10 milliamps if we can do it. Or maybe simply 1 milliamp if we can do it. So we want to bring this as low as possible. So this is 1 milliamp, and we have a voltage of 1.12 volts. So you're going to enter those readings down, but don't forget you're entering the current in amperes because you want the slope to be in ohms. So keep that in mind. So for 1.0 amps, we have 1.12 volts. And let's bring it to 1.5 amps. So we have 1.5 amps, we have 1.63 volts. So we will work in increments of 1.5 milliamps, from now on. So we have 3.0 milliamps. Let's see if we can get that right, or get that precise. So that's 3.0 milliamps, 3.21, or 3.20 we'll go with volts. And then we want to go to 4.5. So we have 4.5 milliamps, 4.82 volts. So now we're going to bring this up to 6. So that's 6.0 milliamps, 6.43 volts. $7.5 milliamps, 8.04 volts. $9.0 milliamps, 9.57 volts. $10.5 milliamps, 11.18 volts. $12.0 milliamps, 12.76 volts. And that is as far as we can go with this multimeter. We can't get all the way up to 15 with this multimeter, but that's fine. We'll do one last reading. So that's 12.9 milliamps and 13.65 volts. So that'll be the last reading. And so you're going to plug those values in and put those into your table, and you're going to make a graph. You're going to plot voltage versus current, include error bars on the graph, get the slope of the graph. Again, the slope of the graph should equal the resistance and the uncertainty in your slope reading. And if you're having troubles with the figuring out how to use Excel to get the uncertainty in the slope, please let me know. And then figure out if that agrees with your DMM reading within the uncertainty. Okay, so that's part 2 of the experiment.